cover section 4.2. 4.2 is very long. I'm going to split it into two groups. Essentially, classifying chemical reactions up to everything except for redox reactions, and then the rest is going to be about redox reactions. So that is oxidation reduction reactions. So let us get started. Classifying chemical reactions. Define three common types of chemical reactions: precipitation, acid-base, and oxidation reduction. Classify chemical reactions as to one of these three types given appropriate descriptions or chemical equations. Identify common acids and bases. Predict the solubility of common inorganic compounds by using solubility rules, and compute the oxidation states for elements and compounds. Okay, a precipitation reaction is one in which dissolved substances react to form one or more solid products, also known as double displacement, double replacement, or metathesis reaction. So I want you to remember those words, especially metathesis and double displacement. Many reactions of this type involve the exchange of ions between ionic compounds in aqueous solution. Precipitation reactions are common in nature and in industry. Solubility. The maximum concentration of a substance that can be achieved under specific conditions. The substances that have a relatively large solubility are said to be soluble. A substance will precipitate when solution conditions are such that its concentration exceeds its solubility. Substances that have a relatively low solubility are said to be insoluble, and these are substances that readily precipitate from solution. The perfect example of this is calcium chloride and sodium sulfate, both of which are soluble compounds. When they're mixed together, they form calcium sulfate and sodium chloride. Sodium chloride is a very soluble compound, and calcium sulfate, also known as gypsum, is a very insoluble compound, and it falls immediately out of solution. Okay, I changed this a little bit to be consistent with what I know and a previous table that was used from another text. But this is the solubility rules, okay? The most important thing to recognize is that the most soluble compounds are compounds made of the group 1 metal cations, that's sodium, potassium, lithium, and the ammonium ion. On the anion side are the halide ions: nitrate, acetate, bicarbonate, and chlorate are soluble, and the sulfate ion is oftentimes soluble. So essentially there are no exceptions to the group 1 metal cations. All of them are soluble, and the ammonium ions. Any compound that's ammonium chloride, ammonium carbonate, sodium carbonate, sodium chloride, these are all soluble compounds. Of the halides, almost all of them are soluble, with these few exceptions: silver, lead, and this one is mercury 1. I know it's kind of confusing because it's got a 2 there, but you got to understand that this double cation is spread between the two atoms, and so each one has a charge of +1. And the sulfate ion has the exceptions: of the same exceptions up here for the halides, but it's silver, mercury 1, lead, but also calcium and strontium, and barium. The acetate, bicarbonate, nitrate, and chlorate have no exceptions. So group 1 metal cations and ammonium, acetate, bicarbonate, nitrate, chlorate ions, any compounds that contain these are soluble. The halides are mostly soluble, and the sulfates are mostly soluble with these exceptions. Now, whenever you come across a carbonate, chromate, phosphate, hydroxide, or sulfide, expect it to be insoluble, with the exception of those of group 1 metal cations. So, with the exception of sodium hydroxide, lithium hydroxide, potassium hydroxide, all the other hydroxides are going to be insoluble, like chromium and magnesium and copper and titanium. So titanium carbonate, titanium chromate, lead phosphate, iron phosphate, all of these are insoluble, with a few exceptions, okay? Of course, thus, because these are always soluble, that represents an exception down here. But it turns out that for hydroxide and sulfide, most of the group 2s are also soluble. So calcium sulfide is used widely as a tick remover for dogs. Calcium hydroxide can be used to remove carbonate from carbon dioxide from the air. So this is an important table. It's most important to remember that the first column of the periodic table is all soluble compounds, and that halides are mostly soluble, sulfates are mostly soluble, carbonates and hydroxides are mostly not soluble. Okay, so here are some precipitation reactions. Potassium iodide, aqueous, it's got a potassium which makes it soluble, plus lead nitrate, nitrate's one of those that is always soluble, combine to form lead iodide, that's one of the ones that's insoluble, lead and a halide, and potassium nitrate, which of course is soluble on both counts of both the group 1 and the nitrate. Lead iodide precipitates from the solution, which is consistent with the solubility rules. The net ionic equation, which we've already looked at, lead ions, aqueous, plus 2 iodine ions, aqueous, goes to lead iodine solid. And that just shows you what it looks like. Consider the molecular equation of sodium chloride. Again, sodium is always soluble. Chloride is usually soluble except for lead and what was the other one? Silver. Yeah, there's one more, but plus silver nitrate, which is soluble because of the nitrate, goes to silver chloride and sodium nitrate, which has the net ionic equation of a silver ion plus chlorine ion in solution goes to silver chloride, which is solid, which falls out of solution. Okay, so that's precipitation reactions, also known as metathesis reactions or double displacement reactions. Now we've got the next group of reactions, which are called acid-base reactions. An acid-base reaction is one in which a hydrogen ion, H+, is transferred from one chemical species to another. An acid is a substance that will dissolve in water to yield, let's just call it the hydrogen ion. The hydrogen ion also associates with water, so water is H2O with no charge. So the H plus associates with water and forms what's called the hydronium ion. So it's more often found in solution as a hydronium ion, but actually talking about it as the hydrogen ion or the hydronium ion is essentially equivalent. And let's just say that in water this is what it really is, but we talk about it as a hydrogen ion. So the example is hydrochloric acid is a strong acid. HCl aqueous plus H2O aqueous yields the chloride ion and the hydrogen ion, but in water the hydrogen ion associates with the water and forms the hydronium ion. This is an acid-base reaction. Hydrogen ions are transferred from HCl molecules to the H2O molecule. There could have been much better reactions than this. So this is saying that you've got pure water and you've got gaseous HCl, and that gaseous HCl will get absorbed into the water, leaving chloride ions, water, and hydronium ions. When chlorine gas dissolves in water, it reacts as an acid, transferring protons to the water molecule to yield hydronium ions and solvated chloride ions. Virtually every hydrochloric acid molecule that dissolves in water will undergo this reaction. Acids that completely react in this fashion are called strong acids. And these are the common strong acids. HCl is also called muriatic acid, and maybe you use that in treating swimming pools. Hydrobromous acid is not used that often in ordinary daily life, nor hydroiodic acid. Nitric acid is a little bit on the dangerous side because it can be used to make explosives, so it's fairly regulated. Again, I can't think of a common use for that. And actually the same is true for perchloric acid, because perchloric can be used to make explosives as well. But sulfuric acid is used to open drains. You can buy that in the hardware store. A far greater number of compounds behave as weak acids and only partially react with water. A large majority of dissolved molecules remain in their original form, and only a relatively small amount of hydronium ions are generated. So the most common one of these that we come across is acetic acid or vinegar. And we have acetic acid plus water will dissociate into acetate ions and the hydronium ion, but it goes in both directions. This is only partial, and you could add more acid here and drive it in this direction, or you could add more water and drive it in this direction, dilute it. Only about 1% of acetic acid molecules are present in the ionized form. Of course, that depends on the concentration in water. The use of the double arrow in the equation denotes the partial reaction aspect of this process. We call that an equilibrium. This is also an acid-base reaction. Fruits such as oranges, lemon, and grapefruits contain the weak acid citric acid. Vinegars contain the weak acid acetic acid. Hydrogen atoms that may be transferred during an acid-base reaction are highlighted in the inset molecular structure. They don't do a really good job of what citric acid looks like here, but this is acetic acid. That's the active hydrogen. In this case, the hydrogens that are attached to oxygens here are the active ones, and these attached to the carbons are not. A base is a substance that will dissolve in water to yield hydroxide ions, or OH minus. The most common bases are inorganic compounds composed of alkali or alkaline earth metals, groups 1 or 2, combined with the hydroxide ion. For instance, sodium, potassium, calcium, and barium. They don't put magnesium on here because magnesium hydroxide is insoluble in water. These bases, along with other hydroxides, completely dissociate into water and are considered strong bases. What we're going to talk about also is some compounds don't actually carry OH, but end up producing hydroxide in water anyway. So sodium hydroxide, solid, is mixed with water and it breaks into sodium ions and hydroxide ions that are aqueous. The dissolution process is essentially complete when sodium hydroxide is dissolved in water. The process is dissociation, a physical process, and not an acid-base reaction, meaning that it didn't actually change a water molecule in the case of an acid. Some compounds produce hydroxide ions when dissolved by chemically reacting with water molecules. In all cases, these compounds react only partially and are classified as weak bases. So, example is ammonia. Ammonia, aqueous, plus water, liquid, goes to ammonium ions and hydroxide ions that are aqueous. This is an acid-base reaction. H plus is transferred from water molecules to ammonia molecules. Ammonia is a weak base used in a variety of applications. Pure ammonia is used on the agricultural fields, corn, soybeans. Well, corn, soybeans actually put nitrogen in the soil also. And of course it's used for cleaning. Now, that's an acid-base reaction, but this is another type of acid-base reaction, and that's called a neutralization reaction. A neutralization is a specific type of acid-base reaction in which the reactants are an acid and a base. The products are often a type of salt and water, and neither reactant is the water itself. So, when we say salt, we don't necessarily mean sodium chloride, although we could mean that. It simply means an ionic compound. That's all that salt means in this case, is that it's an ionic compound. So, an acid plus a base goes to an ionic compound plus water. Now, if that's a soluble ionic compound, then the net ionic equation will always be the anion of the acid plus the cation of the base the net ionic equation will always be, for a neutralization reaction, hydronium plus hydroxide, OH minus, yields H2O, or 2H2O if you start with hydronium. So we have magnesium hydroxide, that's the base, 2HCl aqueous, that's the acid. Magnesium hydroxide happens to be insoluble. Goes to magnesium chloride, which is soluble, plus 2H2O. Liquid. Magnesium chloride is a salt. So it just says that it's common practice to put lemon on fish because it takes away some of the fishy smell, which tends to be an alkaline material. So you use acid to convert the alkaline material into a salt. Aha! We're beginning redox reactions. And at that point, let's stop this. Okay, we're halfway through the slides. Redox reactions are important. We need to talk about oxidation numbers and reactions in which oxidation numbers change. And reactions in which oxidation numbers change are redox reactions. Okay, that's it for today. Thank you for listening. Yep, that didn't do it.